Alright, so now we're here. We're going to add a couple more rules. So far we've got the constant rule, derivative of a constant is 0. The power rule, where you take your power, multiply it times the coefficient, and then subtract 1. So now we're going to do sum and difference and the k constant rule, or also known as the constant multiplier rule. I changed it to a k to differentiate it from the constant rule that we've already done. So this is the constant multiplier rule. Alright, so just like we did before, we're going to show you what the rules are here, and then we're going to go and basically kind of do the proof for them on your own paper. So we have the derivative of the sum or difference of two functions. The derivative of a sum is the sum of the derivatives. Easy peasy. The derivative of a difference is the difference of the derivatives. And so this is actually kind of nice because it sort of follows the limit rules that we were following before. And then just like limits, the derivative of a constant multiplied in front of a function is the constant multiplied in front of the derivative, that you can basically just factor it out. Alright, so let's come over here because we have to prove everything that we've done. So now we're going to basically prove, let's do the sum and difference rule. Sum, difference, I'm going to do those together. Alright, so we have our function f of x plus g of x. Alright, let's just call it y. Or if you want to have our h of x, but remember that our derivative rule, to find y prime, you're going to take the limit as h goes to 0. We're going to take the function, which happens to be, we'll do plus or minus. We're going to plug in x plus h, so that would be f of x plus h plus or minus g of x plus h. Then we're going to subtract f of x, the function itself, plus g of x, and that's all over h. So just following our little rule down. Now I'm going to creatively rearrange that. Basically what you can do with this is I can rearrange this. That this part right here, I'm going to subtract f of x. So I'm going to move that over to here. Okay? So this is going to be the limit as h goes to 0 of f of x plus h minus this f of x. Okay. Then I have plus or minus, here's the g of x plus h. Now it's going to be minus another plus or minus, which kind of flips it. You could actually kind of do it this way, reorder it, because now I have the plus or minus out here, g of x, all over h. So I'm grouping these two together and these two together. Put the f's together, put the g's together. Now when you do that, if you think about what we have a fraction over a common denominator. I can split the fraction, because I have a single denominator, to be f of x plus h minus f of x over h plus or minus g of x plus h minus g of x all over h. And so now we have the limit of a sum or difference, which according to our limit properties, we can distribute the limit. So I have the limit with the f's plus or minus the limit with the g's. And hopefully you will recognize that, hey, this is nothing more than the derivative of f plus or minus the derivative of g. And we have our sum and difference rule. So just simply by doing a little creative rearranging, we managed to come up with our little shortcut rule. And then our last one over here, our constant multiplier rule. Constant, I'll use the k again to show the difference. Constant rule. That if my function is a constant times f of x, and I want to find the derivative y prime, then I'm going to do the limit as h goes to 0 of k times, plug in your x plus h, minus your function, all over h, and hopefully you can quickly see that you can factor out to k and have f of x plus h minus f of x all over h. And the limit of a constant times anything is the constant times the limit. We can pull it all the way out. And what we have here is nothing more than k times the derivative. So a constant multiplier, if I want to take the derivative of a constant multiplied times a function, I can simply take the constant times the derivative of the function and pull it out. So that gives us our constant rule. All right, so now let's do a couple practice problems using these rules. I want to find the derivative. This is very helpful when you have polynomials, because when I have the sum or difference of power functions, I can use power rule and I can just run it right through, and we can very quickly go, hey, the derivative of this is going to be derivative of x cubed, 3x squared, derivative of minus 4x, minus 4, derivative of plus 5, plus 0, so we end up with 3x squared minus 4, and we raise our hands and cheer a little bit because it was a lot less work than the limit definition. Here, can we just kind of think of this as negative 1/2 times? So I should be able to run through with the derivative. 4 times negative 1/2 is negative 2x cubed, my 6x squared minus my 5, and we're done, and we're going to walk away from that one. Here, got to do a little rewrite. You simplify early, simplify often. You have to get this in the sum or difference of power. Sum difference of power and constants. So when you see something like this right now, because we don't have a rule for a quotient like this, we're going to rewrite this, and we're going to remember that we can split fractions. And I'm going to come right down here for this one, that I can rewrite this as y equals 2x cubed over 2x to the 1/2 minus 3x squared over 2x to the 1/2 plus 7x over 2x to the 1/2 plus 5 over 2x to the 1/2, which is then going to allow me to rewrite this using the fact that you subtract your exponents, cancel your 2's. This one would be x to the 3 minus 1/2, which would be 6/2 minus 1/2, 5/2, minus 3/2 x to the 2 minus 1/2, 3/2, plus 7/2 x to the 1 minus 1/2, 1/2, plus 5/2 x to the negative 1/2. Rewrite early and rewrite often. You have to get it as a sum or difference of power rules. And then we can take the derivative. So y prime, notice I'm switching here, y equals. Now I'm ready to take the derivative. Maybe if you want, you can draw a little line in between here. So hey, I'm doing the derivative now. Y prime would be 5/2 x subtract 1, 3/2, minus 9/4 x to the subtract 1, 1/2, plus 7/4 x to the negative 1/2 plus negative 5/4 x to the negative 3/2. And so the idea here is that you can very quickly get a derivative, but you have to rewrite it, and it has to be the sum or difference of power functions. Same thing here. We see something like this. We do not know anything about the derivative of a product or a square like this. So what we're going to need to do here is we got to rewrite it as the sum or difference of power and constants. So we got to do a little algebra, but you have to multiply it out. So I'm going to FOIL this out. This would be 9x squared plus 12x plus 4. Run the x through. So y equals 9x cubed plus 12x squared plus 4x. And once we get it to here, now we have it in the form that's going to allow us to take the derivative. So let's do dy dx this time. So 3 times 9, 27x squared plus 24x plus 4, and we have our derivative. Simplify early, simplify often. and look to see if you can rewrite it as the sum or difference of power and constants, because those are the shortcut rules that we know so far. Okay. All right, so example 8. So we have a nice polynomial here, and we want to find the coordinates and equations of any horizontal tangents. Why is this going to be important? Horizontal tangents would be the places where you have a slope of 0. What's going to be important, and we're going to really stress this a little bit later, this is going to be the location where you have possible extrema, where you may have a global min or a global max. See, back when we were in pre-calculus, we could factor and find x-intercepts, but we could not actually find the maxes or mins, the local maxes or mins, without using our calculator to say, calculator, hey, estimate this for me. Now you're going to be able to basically do some algebra, do some calculus, in order to determine where those possible extrema are going to lie. So what do I need to find? The horizontal tangents. First thing I need to do is I got to find f prime of x and figure out where that's equal to 0. Okay. So I'm going to find, or in this, since I have y here, maybe I want to write it as dy dx is equal to 0. So I first find the derivative, dy dx, 4x cubed minus 4x. And the nice thing about that is my horizontal tangents are when dy dx is equal to 0. So I set the formula we just found, equal to 0. It involves a little factoring. Let's take out a GCF, 4x. We're left with x squared minus 1. So x equals 0, x equals 1, and x equals negative 1. So those would be the locations, the x values. Now I need to go calculate the y values. So f of 0, and we'll come back to here. Okay. You want to use y equal to f of x to find the y coordinates. A common mistake that I see is students sometimes then plug these back into here and then they get confused. You go back to the original. I plug in 0, I get 2. F of 1 is 1 minus 2 plus 2, or 1. And f of negative 1 is going to be 1 minus 2 plus 2, which is 1 again. So my coordinates are going to be 0, 2, 1, 1, and negative 1, 1. And then it also said to find the equations of the horizontal tangents. Now wait a minute, to find the equation I also need the slopes. The slopes you find using f prime of x. So notice that here to find the y values I had to use f of x, but to find the slopes I have to do f prime of x. So I'm going to calculate in each case f prime of 0 to get the slope here, which is going to be 0. You feel like, oh, wait a minute, these were horizontal tangents. F prime of 1 is 0, and f prime of negative 1 should be 0. Otherwise, we've done something wrong here, because these were horizontal tangents. So our equations of the tangent lines are very easy, since they are horizontal lines, which are the form y equals. So we would have y equals 2, y equals 1, and y equals 1. If we take a look at the picture, just to kind of verify what we have found out here, if we take a look at this on our calculator, so we had x to the 4th. Just clear out all of these. So we had x to the 4th minus 2x squared plus 2. And then if we take a look at the graph, let's just try zoom 6 standard, see what that looks like. And you'll notice that on this graph I have 1, 2, 3 extrema. If I hit trace and I type in negative 1, there's a location of 1 extrema, y value of 1. Type in your 0, 0, 2, and then type in your 1, 1, 1 again. So you can see where we have the horizontal tangents is exactly where we had the extrema, where we were changing our direction from positive to negative.